This video will walk you through the examples from the Chapter 5 PowerPoint slides using Excel. So the first one we're going to start with is the Telemark example. It's about telemarketing. We have 20 employees. The dependent variable is the average number of days average number of calls per day over the last 20 work days. And X is the number of months on the job. So we're looking at number of months on the job to predict calls. And I've gone ahead and I've run just a plain linear regression initially here. And I'm going to label it linear. So the first thing we want to do, let's make sure by doing a scatter plot that, a transformation really is needed. So I'm going to highlight my X and Y data, and I have it in X then Y. So I can just go right into Insert and Scatter Plot. And I can see here a bit of a curvilinear relationship that definitely develops as the number of months on the job increases. The number of calls also seems to increase, but at a slightly decreasing rate. So that's going to tell me that this is probably a quadratic relationship. In other words, that my X variable should probably be squared. So what I'm going to do is I'm going to insert in here months squared. And then I'm going to create that variable. So equals months squared. And carry that down for all of my other observations. Now, I'm going to rerun my regression. So data analysis, regression. My Y range is going to be my calls. And my X range is going to be both months and months squared. So this is important. When you're doing a polynomial transformation, so squaring, cubing, raising something to the fourth, something like that, you need to always include all of the lower powers as well in order to run your regression. And I need to put this, I can't put it in E1, I already have something there, I don't want to overwrite it, so I'm going to put it in M1. And look at my output there, and I'll call this my quadratic regression. Okay, so let's see if my quadratic regression is in fact better. So the first two things I'm going to compare are the R squared and adjusted R squareds. We want these to go up because the R squared shows us the percentage of variation in our dependent variable explained by our regression. So our R squared did in fact go up, so that's a good thing, and our adjusted R squared went up as well. The next thing we want to check are our standard errors. We want standard error, or the amount of misses, to go down. So did our standard error go down? Yes, our standard error did go down, so that's good. Then we want to look at the p-value of our variable of interest here. And so for the quadratic transformation, I really want to look at the p-value of months squared. I don't really care about months anymore. I just want to look at the p-value of months squared. And I see that that is in fact statistically significant. So I'm going to say that, this probably was an appropriate transformation and that this is going to be good. I can also confirm that idea by looking at a new scatter plot. So insert scatter plot, and again, now I have them in X and Y notation. And I have this months squared and called. That looks a lot more like a linear relationship that I'm seeing there. So I'm going to say that this was, a good transformation. So now we're going to move on to the highway miles per gallon example. This is a reciprocal transformation example. We are looking here at highway miles per gallon for 150 cars and their horsepower. And again, I've gone ahead and run the linear regression already. And we believe that there is an inverse relationship between highway miles per gallon and horsepower. So I need to create the inverse variable. So 1 over horsepower. Horsepower is going to be my independent variable. Now, the first thing I might want to do, let me just insert this in here. So first thing I might want to do is go ahead and look at what my scatter plot would look like. But my dependent variable is highway miles per gallon and my independent variable is horsepower. So I can't just go ahead and hit insert scatter plot and expect that to show up. I would have to go through here, rearrange them to x then y notation. And here I can see that inverse relationship, developing. So I'm going to want to go ahead, let me bring this back over here, and create my reciprocal of horsepower. So 1 over horsepower equals 1 over horsepower. Sorry, equals 1 over, and click on the horsepower. Don't know why I did that. Okay, and drag that down, or apply that all the way down. Label this my linear. Okay, and I'm going to rerun this regression now. So data analysis, regression. My y range is going to be my highway miles per gallon. My x range is going to be my reciprocal of my horsepower. Now, unlike the polynomial transformations, when you do a reciprocal transformation, you do not include the pre-transformed variable. So I'm only going to include that reciprocal variable there. And now I want to place my data in N1 over here. Place my output there. Alright, so I'm going to check the same things in my reciprocal. In my reciprocal regression, I want to see, did my r squared increase? Okay, so my r squared originally was 59%, and now it's raised to 80%. So that looks really good. I also want to make sure that my standard error decreased. Let's look at my standard error here. And yes, my standard error did in fact decrease. And then what about the p-value on my principal independent variable? Is that still statistically significant? Yes, it is still statistically significant. So that's going to tell me that this was an appropriate transformation. The other way I can look at this, I can insert another column in here too, and I can look at that scatter plot again. So my x variable is my 1 over horsepower. My y variable is my highway miles per gallon, so I can arrange them x then y. Then insert a scatter plot there to compare. And here I see much more of a linear relationship that is clearly developing. So that shows me that that was an appropriate transformation to make. Okay, the last one I'm going to show you is this imports versus GDP example about using logarithmic transformations. Now, there are several different logarithmic transformations that you can do. You can log x, or you can log y, or you can log both. The way that you determine which one you want to log is by doing that initial scatter plot. And here we are going to have our GDP as our x variable. So again, I'm going to have to move this over in order to create my scatter plot. Okay, insert. And again, the reason I'm doing that each time is just because we need to be in X then Y order in order for Excel to just go ahead and do the scatter plot just by highlighting our data. But now it looks crappy, so I'm going to put it back. Okay, so I'm going to look at that, and when I look here, I see it looks clumpy on both the X and Y axis. If it looked clumpy only on the X, then I would do a logarithmic transformation of X. If it looked only clumpy on the Y axis, I would do a logarithmic transformation only on the Y axis. But here it looks clumpy on both, so I'm going to do logarithmic transformations of both. So let me insert a couple more columns here and create these new variables. So the natural log of imports and also the natural log of GDP. Okay. The way I'm going to create that just equals ln and then highlight, click on my import and bring that down. Do the same thing for my GDP. And bring that down. Now I can go ahead and run my logarithmic transformation regression. So regression, my dependent variable is going to be imports, but now it's going to be the log of imports. So I'll highlight ln imports. And then my independent variable is going to be the natural log of GDP. And again, I logged both because it was clumpy on both axes. And I'm going to put this in any open cell here. Now, we've gotten used to automatically saying, okay, I'm going to check the R squared, adjusted R squared, standard error, and p-values. It's a little bit different when you're doing logarithmic transformations. We can see here, if we were to go and look at those, it actually looks like, our regression is worse because our R squared went down. Although our standard error, and R squared going down is a bad thing, our standard error also went down, and standard error going down is a good thing. But, we're getting mixed messages here. It's a little confusing. How do I know that that was definitely the appropriate kind of transformation? Well, the first thing I can do is actually look at that scatter plot again, and I'll see that this relationship was more appropriate. Remember, when you're doing a logarithm, it's the rate of change of the rate of change. So here, this is a much more linear type relationship. So it's much more appropriate, to run a linear regression, obviously, when you have a linear relationship. So we've transformed this nonlinear relationship into a linear relationship via this logarithmic transformation, and that's going to allow us to use this regression to make interpretations and predictions. But be careful when you are making interpretations and predictions using logarithmic transformations. So normally, if I were to look at this untransformed regression, my linear regression, my untransformed regression, I would say for every $1 increase in GDP, imports are predicted to increase by 0.10. Okay, I cannot say that in the same way for my logarithmic transformation. Instead, I have to undo that logarithm. So equals exp, so the exponential undoes the natural logarithm. So in order to interpret this now, I would say for every $1 increase in GDP, imports are predicted to increase by 2.37 or 2.38. Okay, so always remember when you're doing your interpretations to, undo the natural logs via the exponentials. The same thing will occur if I want to make a prediction. Let's say I want to predict the imports when you have a GDP of 3.5. Okay, so if I want to do that, normally I would just say intercept plus 3.5 times my, intercept plus 3.5 times my beta coefficient. However, I can't just put in that 3.5 normally. I'll have to take the natural log of that 3.5 and then multiply that by my beta coefficient to get my prediction, and then I will need to take the exponential of that because the answer it's going to give me is going to be in a natural log, and in order to actually get that back into a value that I can interpret, I would have to undo my natural logs that I'm doing. So just be careful about the interpretations and predictions when you do logarithmic transformations.